Okay, so now we're left to really just show that that L sub 5 complement is context-free. And so remember, the reason why we're doing that is because if we show that L sub 5 complement is context-free, then because all of this is regular, we get that, regular union context-free, that's context-free. So we get that Val-comp's whole complement is context-free. And that means that we can create a context-free grammar G that generates Val-comp's whole complement based on some arbitrary instance of M and X. And so that gives us a mapping reduction from the not halting problem to the all CF problem. So believe it or not, what this is actually part of is it's still actually part of the mapping reduction, right? So really, this is the instance modification part of mapping reduction. We're describing how we can actually create a context-free grammar G that generates Val-comp's whole complement, right? And so, well, these guys are regular, right? These guys are regular. So there's right linear grammars that generate them. And so we can just use those right linear grammars. And because a right linear grammar is context-free grammar, then we can just sort of union their production rules together. The only thing we actually have to handle now is to show that this guy is also context-free. And so instead of designing a context-free grammar, which generates L5 complement, that's a bit trickier. And so what we're going to do instead is we're going to design a PDA. And that's good enough because you can convert a PDA to a context-free grammar because these two things are computationally equivalent. So we never actually saw the conversion algorithm in class because it takes like a lecture to describe and it's very boring and annoying, but there is a conversion algorithm and so it can be done. So we want to show that L5 complement is context-free, and to do that, we're going to design a PDA P such that the language accepted by P or recognized by P is L5 complement. Well, let's first think about what L5 complement is. So if I have a string in delta star, remember delta is the alphabet in this case, and that string is in L5 complement. Well, by definition, that means that that string is not in L5. So that means that the condition C5 is violated somehow. And for the condition C5 to be violated, it means that that whole string alpha has at some point some consecutive alpha I plus 1, where the alpha I plus 1 doesn't follow from the alpha I with the rules of the transition function of M, right? So that means that there exists a pair of consecutive alphas, alpha I plus 1, such that alpha I does not actually give you, in one step of the transition function of M, alpha I plus 1, right? And so the idea is that the idea of the PDA, so this is the general high-level idea, the PDA will search for such a pair of alpha I plus 1. If it finds this pair, then it accepts. So it goes to an accept state. And if it can't, right, if it can't find such a pair, it will never get to an accept state. Get to accept. And so effectively, that means that that string is rejected. Right? So that means that that string is rejected. Right, and remember, PDA has this very important tool known as non-determinism. So here, when I talk about PDAs, I really mean NPDAs. And remember that NPDAs are actually much more powerful than deterministic PDAs. And that's because NPDAs can make guesses and they can verify their guesses, much like NFAs. But in the space of PDAs, non-determinism actually helps a lot, and it allows them to accept many more languages than DPDAs. Okay. And so that's essentially the high-level idea of what we're going to do. We're going to Okay, so how can we actually implement this high-level idea with a PDA? Well, consider our PDA, right? So we have our PDA, PDP. We have our PDA P, okay? And what our PDAP does is it scans this input string alpha, right? So remember, now we're dealing with a PDA, okay? Not a Turing machine, a PDA. So, you know, it has a hash, then alpha 1, or alpha 0 rather, then alpha 1, and so on. And then maybe at some point it has this violating pair of alphas, right? So, you know, you have alpha I and alpha I plus 1, which violate the rules of the transition function, or the rules of the next one instantaneous configuration relation, really. Okay. So how can P actually manage to find that pair of alpha I plus 1? Well, it guesses, right? The power of non-determinism is that you have the ability to guess and then check your guess. And if you didn't guess right, then just guess again later. If you did guess right, then that's an accept, right? So, you know, P scans through the string, and maybe at this hash, it guesses that it's going to see the incorrect pair of alphas, and it guesses wrong, so it moves on. And then it keeps guessing, and then at this hash, it guesses that it's at the incorrect pair of alphas, and then it verifies its guess, right? So every time it guesses, right? Every time it guesses at a hash, right? So at a hash, it guesses that alpha I is the first of the inconsistent alpha I plus 1. Okay? Because remember, for the PDAP to accept, it has to find a pair, right? It has to find a pair of alphas for which they violate this relation, right? So for which this is not true. It is not true that you get in one step with the rules of M alpha I plus 1, right? So there's a violation in this next one instantaneous configuration relation. Okay, and so suppose it guesses that that's alpha I, right? Suppose it guesses that alpha I is the first of that pair. Then what it needs to do for the rest of the string is it needs to verify. It needs to verify this guess. Okay. And how does it verify this guess? Well, it considers the cases that could lead to a violation. Right? So what cases lead to a violation? So it considers those cases, and you know, it guesses which one it is, and it sees whether that violation is in alpha I plus 1. If it is, then it accepts. If it isn't, then it guesses again. Okay. And it keeps guessing throughout the string. If it can never make a correct guess, then it rejects, because it means that alpha was not in L5 complement to begin with. If it does find a pair where there's this violation, then that means that because there's a violation in the condition C5, then alpha is not in L5, which means by definition that alpha is in L5 complement. Okay, so what cases lead to a violation? Or, yeah, to a violation, not to a violations. Okay, well, there's two real cases. Well, there's two main cases. So case one is the transition function delta of the Turing machine is not respected. Okay, well, what could that look like, right? What could that look like? Suppose I have, you know, a string, then I have my hash, then I have, you know, the part of the beginning of the string alpha I, and then I have the part with the pointer, right? The part with the state. So I have, you know, B Q1A, and then I have the rest of the string and a hash. So this is alpha I. And then I have another string, right? I have the other string alpha I plus 1. I plus 1. Which in the corresponding window with the pointer is perhaps Q2BB, right? And maybe this is the incorrect guess. So why could this be or not the incorrect guess? Maybe this is the violation. So why could this be the violation? Well, maybe delta of M said that if M was in state Q1 and reading an A, then it would return state Q2, it would write an A, and it would move left, right? And so if you look at alpha I plus 1, it doesn't look like that's what's occurred, right? Because what would have to happen is, Q1 would read this A, it would write an A, and it would move left, and it would be in state Q2. But what's happened here is that we have Q2BB, so what the string shows is that the machine incorrectly wrote a B instead of an A, right? So this is not what the machine should have done, because this is what delta says the machine should have done, and M, remember, is deterministic in this case, so there's no other possibility. So this is a violation, right? So this is a violation. This is a violation because B is written instead of A. Okay, so that's the first type of violation. That's the first case where essentially there's a violation in the transition function of M, right? From alpha I to alpha I plus 1. The other possibility, the other case where we have a violation where alpha I and alpha I plus 1 don't respect the next one instantaneous configuration relation is case 2. And so in case 2, we can just label this or say that this is a miscopying. Okay. And so what do we really mean by that? Well, suppose that in this case, so in this pair of alpha i's and alpha I plus 1, the rules of the transition function of M were respected. In other words, so you had the B, Q1, and A, and you had the correct corresponding 3-letter window. So you had, Q2, B, and then A, right? So this is good, right? This is okay. But maybe somewhere here, right? Maybe somewhere here, maybe 10 letters away from the hash, alpha I had an A, and maybe 10 steps away from the hash for alpha I plus 1, it had a B, right? And so what's happened is that this letter has been miscopied. So miscopied letter. And so that's another violation, right? Because in instantaneous configurations, the only thing that changes is this 3-letter window, right? That's the only thing that can change. Okay, so these are the two cases that can lead to a violation. And so then what the PDA has to do is it has to scan through, it has to scan through the string, right? It has to scan through the string. It guesses where it thinks the violation occurs, and then it scans through the string alpha I, and it guesses the 3-letter window, right? Because alpha I and alpha I plus 1 can only change within a 3-letter window, right? And so logically, what the PDA has to do is it has to scan through the string, but sort of using a 3-letter window, right? So it scans the first part with a 3-letter window, the second, the third, and so on. And so it guesses which 3-letter window is the one that, is either miscopied or causes a violation in delta. Right? And so it guesses the 3-letter window, and then it verifies the guess in the corresponding alpha I plus 1. So that's what it does. Now, how does it actually do that? Well, it relies on 2 main ideas, right? The first main idea is going to be how you can actually match a 3-letter window which is miscopied, okay? And how you can match a 3-letter window which violates delta. So that's the first idea. And the second idea is slightly more subtle. It's if you can do this matching, right? If you can just do this matching of 3-letter windows, you have to make sure that you're doing it from the same distance from the hash, right? And so the second idea is going to be, yes, you can sort of check 3 letters for 3 letters in alpha I and alpha I plus 1, but you also have to check that they're the same distance from the hash. And that's where the actual stack is going to come in. That's how you're actually going to be using the push down automata. Okay, because before that, when I'm describing before that, when I'm just saying matching 3 letters for 3 letters, you could just use an FA for that, really. Okay, and so how can, so essentially, the question becomes, how can a PDA detect and verify case 1 or case 2? And so to do this, it relies on 2 main ideas. Okay, the first idea 1, is, well, suppose you have alpha I and alpha I plus 1. Okay, and alpha I has this 3-letter window, X. So X is 3 letters. Maybe the state, and then 2 tape letters, which causes a violation. So which is either a miscopying or a violation in delta, right? So that means that in the corresponding alpha I plus 1, corresponding meaning from the same distance, or of the same distance from the hash, you have another 3-letter window, right? So both of these are 3-letter windows, which I'll abbreviate 3-letter window, where there's either, X and Y are either causing a miscopying, or they're causing delta to not be respected. Okay, and so to the left, to the left of X, you have some string U1. To the right, you have some string U2. To the left of Y, you have some string W1, and to the right, you have some string W2. Right, and the restriction here is, of course, the length of U1 is equal to the length of W1, because you need the same distance from the hash in both cases. So the first idea is related to how you're going to actually check that X is mismatched with Y. Okay, so the first idea is related to how you check. So idea 1 is related to checking a mismatch between X and Y. Okay, and fundamentally, this idea relies on something very simple, which is that since gamma, Q, and delta are finite, so gamma and Q being finite, that makes sense. They're sets. Delta being finite, that just means that given an input, there's a finite number of possibilities for delta, right? In fact, there's only one if it's deterministic. So since these 3 things are finite, the PDA, can hard code every possible mismatch. Okay, and this is going to be sort of done in a finite number of states. And so this is okay, because the control unit of the PDA should be finite. Okay, so how can it do this? How can we hard code this? Well, the best way is to illustrate this using the same examples, I would say. So let's consider case 1. So case 1, but now sort of via the PDA, via an actual transition function. So suppose we had, I think our initial example was Yeah, okay, so we had, B, Q1, A, and Q2, B, B. Okay, and this is a mismatch, right? This is where the mismatch occurs. So this is the mismatch because delta Q1A is saying, well, go to Q2 and write an A and move left, right? So the mismatch occurs because of this, right? And so then what you can do is you can hard code this 3-letter window into a branch of the PDA, right? So you have your state just guessed, right? Your state just guessed that it was at the hash, right? It was at this hash which caused a violation, right? It was at the hash where it would be the start of the alpha I plus 1, which caused the violation, right? So, it doesn't do anything to the stack. And now what it does, it runs through, right? It runs through all of the letters in here. It runs through all of the letters in here until it gets to the 3-letter window here. And it's just guessing that that's the correct 3-letter window, right? So in other words, here we need a transition for gamma, right? For gamma, you don't change anything with the stack, and for Q. Right, so this is an abuse of notation, right? I'm abusing notation. I'm just saying that, if gamma is A, B, the blank, and the dash, then this should be, A, B, blank, and the dash. And the same thing goes for Q, right? Okay. And also remember, when I say Q here, I'm talking actually about Q of the Turing machine, not Q of the PDA. So this is Q interpreted as a letter. So make sure you see that these are different from the states of the PDA. Okay. And then at some point, it guesses that it's going to read the 3-letter window, which is going to cause a mismatch here, right? So it reads the 3-letter window. So it reads the B. It reads the Q1. So I'm just going to put the letter because I'm not going to do anything with the stack. And then it reads an A. Okay. And then it's going to move through the rest. It's going to move through the rest of the string, right? So it's going to move through the rest of the string. Right, I'm not putting anything to say that I'm not changing the stack, just for simplicity of notation. Okay. And then at some point it sees the hash, and now once it sees the hash, it's going to verify its guess, right? It's going to verify that this did indeed cause a mismatch, right? So it sees the hash. It sees the hash. And then it looks for this 3-letter window, right? So it looks for this 3-letter window. And so it's looking for the corresponding 3-letter window that violates this one, right? And so what it's going to do, what I'm going to do at this state of the PDA is I'm just going to hard code all of the possibilities, right? So all of the possible mismatches. Okay. So all of these, I'm going to have branches of 3 edges, right? I'm going to have branches of 3 edges where the 3-letter window that you can read off the edges of the branch, right? So imagine, this is Q2BB, right? All of these strings that I can read off the 3 edges here are going to be in, they're going to be in gamma union Q cube minus, so everything except for the actual 3-letter window that would be consistent with this, right? And so in our case, that would be what? That would be Q1 moving left, and then switching to Q2, and then A not being changed. So that would be Q2 B A. Whoops. So there's going to be here one branch for every sort of 3-letter string that looks like this, right? That's in this language. Okay, and that's because those are all the 3-letter windows which mismatch with this guess. Okay. Okay, so that's the case one. That's case one, and really you'll notice that case one is when there's a pointer in the first 3 letters of this window, right? So when there's a state in the first 3 letters of this window. So, you know, another possibility, because this is just one branch, right? This is just one branch. So you have this one branch here, but there's many others, right? There's many others. There's all of the branches here which have at least one state, right? So, you know, maybe there's like A, Q3, and then B. And then it's the same idea. It's copy paste the same idea here and here, except that now you're creating all the possible branches except for the correct one where the 3-letter window is this one, and using delta you get a different 3-letter window. Okay, so hopefully this is clear. I know this is a lot to take in, and this is just for case one, right? And case one is actually a bit harder than case two. Case two maybe will help clarify things a bit more, right? So in case two, what's going on is you have a 3-letter window, but it has nothing to do with the transition function of delta, right? It has nothing to do with not respecting delta. So it's far away. It's far away from any like Q here. So you can imagine, you know, that this was copied correctly, or not copied, but this was the correct corresponding instantaneous configuration for delta, right? For the transition function delta, right? So, you know, the correct one would be A here, right? So supposing again that delta Q1A is Q2 A left, then this is okay, right? This is correct, right? This is correct. But maybe what's not correct is, you know, you have some miscopying here, right? Maybe here you have an A, B, and an A, and then instead here there was a miscopying. So, you know, you had an A, and then an A, and an A. Okay. And notice actually, so some of you are probably confused. I'm not using the stack at this point, right? I'm not actually checking that I'm at the same distance from the hash. I'll do that in a second, right? Right now, I'm just talking about how I can check that a 3-letter window string in alpha I mismatches with a 3-letter window string in alpha I plus 1. Okay. Okay. So there's a mismatch here, right? We have a mismatch. And so then we're going to use the same idea to create a state transition, part of the state transition that guesses this type of case, this type of mismatch case, and then verifies it. Right? And so to do that, you know, it's the same idea. So this part of the diagram is exactly the same, actually. So you can imagine that the PDA is really huge, but this part is the same, right? Because you're guessing at some point, that you're about to read the incorrect alpha I. Okay. And then you say, well, you know, let me read through some parts of the string. So let me read through some parts of the string. Again, I'm simplifying notation here just to say I'm not touching the stack for now. I'll modify this diagram in a second where I will have to use the stack. But for now, you know, I'm just going through the string. I'm going through this string. And then at some point, I find this 3-letter window, which I think is the one that causes the mismatch. So then I read it, right? And there's many, right? There's many possible guesses, right? But this is one. This is one. So I read an A, then a B, and then an A. And then I move through the rest of the string. So I move through the rest of the string. I pass the hash. I move through the rest of the string, the first part of the string here. And then I verify, right? I verify that this is mismatched with this three-letter window, right? And so a mismatch is anything but ABA, right? So here, A is a mismatch, and so is, B, B. So everything here is a mismatch other than, right? So I'm going to have a branch. So one branch for every gamma union Q cube minus the actual correct corresponding three-letter window, which is ABA. Right, so everything except ABA. Okay. And so that's how you guess that you have the three-letter window, which is incorrect. I'm going to lower my hand. Oh, okay. So you guess that you have the incorrect three-letter window, which is causing a mismatch, and then you verify it with the corresponding incorrect three-letter window, right? So all I'm showing here is how to do sort of this idea, right? How to do this idea of guessing this three-letter window, and then checking that it's mismatched with Y. Now there's a problem, right? The problem is that I'm not actually guaranteeing that the verification is done at the same location as X with respect to the hash, right? Because really for this to be correct, I would need to say, okay, I'm going to count until say 10, and then I'm going to read this three-letter window. I'll read the rest of the string, and then here as well, I'll count until 10, and then verify that this Y, right, that this Y is in conflict with this X, right? And so this is where the stack comes into play, right? This is where the stack comes into play, where I'm going to use the stack to push things onto the stack until I guess X. Then I'm going to read through the rest of the string. Once I get to the hash, I'm going to start popping from the stack. And when the stack is empty, only when the stack is empty, I'm going to check that X is actually clashing with Y. Okay, so that's what I'm going to do. So idea two is related to guessing and verifying X and Y at the same distance. Right, it's at. I was using two. At the same distance. From their respective hash. Okay. And so to do this, what I'm going to do is I'm going to use the stack. So to do this, I will use the stack to push until you guess that X is the inconsistent three-letter window. And then pop starting from the next hash. So use the stack to push until you guess that X is the inconsistent three-letter window, and then pop starting from the next hash. Matching Y with X, or verifying really. So you're verifying this Y, this three-letter window Y, verifying the three-letter window Y with X once the stack is empty. Okay. So I guess I need a subject here until the PDA guesses that X is the inconsistent three-letter window, and then pop starting from the next hash, verifying that yeah, okay, exactly, good. All right, so, a lot of words. What does this actually look like? So the idea, I think what I'm going to do is I'm just going to sort of copy this. So it would be the same thing for case one. Because remember, this is all the same PDA, right? So case one and case two aren't actually separate. You have all of the branches for case two here, but then you also have all the branches for case one here. They're all at the same state. Okay. Whoops. You didn't see that? Okay. Right. And so how am I going to do this? Did I copy this correctly? So hopefully now you see why it might have been difficult to do this in person. Yeah, sorry about the people who had to suffer through this. Hopefully it's a bit clearer in the lecture recording. Okay, so it's going to be almost exactly the same thing, right? I'm going to, guess that this is the three-letter window X, which is going to clash with the three-letter window Y, and Y could be any of these. So any of these except for ABA, right? Except that now I have to verify this. I have to verify this when and only when the stack is back to being empty, right? So here the stack starts as empty. And now I'm going to slightly modify this. So I'm going to say on gamma and on Q, I'm going to push something on my stack. So I'll push something on my stack until I make the guess for X, right? So, I make the guess for X. Maybe at this point, my stack has 10 X's, right? So there's 10 X's here. Okay. Then it reads through the rest of the string. And then once it sees the hash, it knows that now it should start popping, right? So here, the stack remains unchanged. So you stopped pushing on the stack. You're not touching the stack anymore. And here you start popping, right? So here, so this is just going to require a bit of surgery here. So here you start popping, right? You start popping the X's from the stack. And once the stack is back to being empty, right? So once the stack is back to being empty, then you actually do the verification, right? So then you actually do the verification. So you make sure the stack is empty. And then you do the verification, right? So you check that the next three letters are anything but ABA, right? So maybe it's A, A, A. Maybe it's B, B, and then A, right? So anything except for, right? Anything except for ABA. Okay. And so if you can do that, then you can move on to an accept stage. Okay. And so this is the idea of the PDA that would, remember what we're trying to do, accept L5 complement. Right. So maybe I think before I end the video, I think I'd just like to give a quick recap of what we just did, because I know this was a lot to consider. So remember what we were trying to do, right? We were trying to show that Valcomb's complement was context-free. And so we know that this part of it is context-free because it's regular. So all we need to do is we need to show that L5 complement is context-free. And so that's what we started doing here, right? So we said that to show that L5 complement is context-free, let's just design a PDA because that's equivalent to creating a context-free grammar, right? And so then the idea of the PDA is, it's given some alpha and it has to check that condition C5 so that this condition C5 is violated, right? And condition C5 being violated means that you have a pair of alpha I plus ones where this is not true, where this does not hold. Okay, so the PDA to do this, well, it's going to make many guesses, right? It's going to read through the string. At every hash, it's going to guess that it's reading the alpha I plus one, which clash with the rules of delta. And to actually do that, right, to actually verify that it's clashing, well, it can consider two cases and only two cases, right? So it scans the string by 3 letters, scans the string by 3 letters, and it's also pushing onto the stack to remember how far it is from the hash. And then at some point it guesses, right? It guesses, it says, oh, I think that this is where there's an incorrect corresponding Y, an incorrect corresponding 3-letter window. So it stops pushing on the stack then, and it moves on to the next string here. So it sees a hash and now it starts popping, right? It stops popping, it starts popping. And then it verifies that there is a mismatch with the corresponding 3-letter window here. And it does that because everything is hard-coded, right? And everything can be hard-coded because there's a finite number of 3-letter windows, right? Because gamma, Q, and delta itself is finite. Okay, and so it makes these guesses, right? And if it's incorrect, right? If it's incorrect, the PDA sort of backtracks. I think backtracks gives you the wrong idea. It's not really like moving its pointer back. There was a comment about this when we were talking about PDAs. What's really going on is it creates multiple copies of itself, right? Where it's trying every possible guess, right? So really it's considering all the possible guesses. And if any of the guesses lead to an accept, then that gives you an accept. If no, then that leads to a reject. Okay. And so altogether, this is how the PDA can accept L5 complement. And so what we're going to do in the next video is just tie things together and show why this shows that the all CF problem, remember, that's what we were actually trying to do. We were trying to show that the all CF problem was undecidable. So why does this actually do that?